Chapter 6 leads us into our discussion of probability in Chapter 7. So Chapter 6 is all about set theory, and Section 6.1 Part 1 starts off talking about sets and set operations. What we really need to do is to be able to communicate, and to do that, we're going to have to talk about a lot of vocabulary, some terminology, notation, those kinds of things. So the very first thing I would like to define is the idea of a set. So a set is a well-defined collection of objects. A well-defined collection of objects. So something that would be well-defined would be the set of students who are in the class that are over 6 feet tall. That's well-defined. We can point to somebody, measure them, tell whether or not they're over 6 feet tall. What would not be well-defined is the set of tall people in the class. And the reason is because what's considered to be tall to me versus what's tall to you could be entirely different things. So each of those elements, or the objects that are in the set, are called an element. So an element is an object in a set. So when we talk about the students in the class who are over 6 feet tall, we could name them, and each of those students would be an element in that set. So we have two different ways of writing sets. So we can write a set using the roster method. This works really well for our class because in general, our sets are going to be countable and listable. So this works well for us. So simply as you list all the elements in the set. So my set could be the vowels in the English alphabet. So that set would be A, E, I, O, U. We won't get into the sometimes Y bit, but that would be the set of vowels. And so I simply list them. You will notice that on the ends of my notation, I have those curved brackets or braces, as we call them. That's how we know it's a set versus an interval or other kinds of things. So when you're writing a set, make sure you include those brackets on the end of it. Another way of doing it, though, is using a set builder notation. This is traditionally used more in a algebra class than our course. So set builder notation. So for instance, if I'm talking about all the numbers that are larger than 1, we could list that as the set of x such that x is greater than or equal to 1. So you'll notice we're using a building of the set by saying x. This little bar means such that x is greater than or equal to 1. So you would build the elements based on this rule in that set. So it uses a rule to describe the set. So set builder notation uses a rule to build the set. Okay, let's keep going with some vocabulary. So two sets are equal, and we talk about equality. So set equality. Two sets are equal. If and only if they contain exactly the same elements. So in other words, if I come in and say that A is the set made up of X, Y, Z, and I say that B is the set Z, Y, X, then I can come in and simply state that A is equal to B because they contain the exact same elements. You don't need to list repeated elements. So if something appears more than once, don't list it more than once. So we can say that A is equal to B. If I let C be the set Z, Y, then we can also say that A does not equal C, or that B does not equal C, because they don't have the same elements. A has something that is not in C. So set equality. Another terminology we're going to use is the idea of a subset. Again, it's all vocabulary. It's a new language. We just need to get used to it. So a subset, the notation we're going to use for a subset is a sideways looking U with a bar underneath it. So that's the notation that means subset. And it simply says that if A is a subset of B, then every element in A is also in B. So every element in A is also in B. So for the example on the board already, we can say that A is a subset of B because every element of A is in B. A is not a subset of C because A contains elements that are not in C. But can I flip that statement around? You bet. I can say that C is a subset of A because every element of C is also in A. So subset simply means the one on the left is fully contained in the one that's on the right. So that they can also be equal and be true because we know that A and B are equal, and every element of A is contained in B. A proper subset. Now we're going to put a more restrictive definition on that. So a proper subset simply says that set A is a proper subset of B if A is a subset of B and B contains elements not in A. In other words, they cannot be equal. In other words, B can't equal A. They can't be equal sets. Now the notation for a proper subset is just the sideways U. It doesn't have the bar underneath it. So I kind of think of this bar as being an equal to, like a less than or equal to kind of symbol. And this is just a less than symbol. So examples of this, let's come in and let A be that XYZ again. I'm going to let C be that ZY again. And then I'm going to pick up a third set D, which is the set, sorry, my braces start they start degrading really quick once I do a lot of them. So D is the set Z, comma, X. So there's 3 different sets on the board. So I can say that the set D is a proper subset of A. D is also a subset of A. So in other words, D is contained within A, and A contains stuff that is not in D. So A contains Y, which is not in D. D is also a subset of A because everything in D is in A. So we can see that they're not equal, but they are, D is contained in A and D is contained in A, and they're not equal to each other, is what this one is saying. So that was a little garbled, sorry. But again, simply means that D is a proper subset of A if A has elements that are not in D. So we already know that D was a subset of A because all of D is contained in A. Now, can I flip these things around? Can I say that A is a proper subset of D? No, that I cannot say because D does not contain elements that are not in A. Can I say that A is a subset of D? No, because A contains elements that are still not in D. So you gotta be really careful about the direction of the conversation that's going on. Okay, just a couple more vocabulary terms. We have something called the empty set, which you're aware of already. It's a set that contains nothing, no elements. So it's a set with no elements. The symbol or notation we use is the circle with a slash through it. You're used to that as being no solution. It means the null set or an empty set. Or you can also use the set of brackets or the braces that are empty. But whatever you do, don't put this inside of that, because then all of a sudden that has an element in it, a symbol. And then finally, our last new word is the universal set. So the universal set. And this is the set of all elements under consideration. Under consideration. We started off with an example of a set V, which was the set of vowels that was part of the English alphabet. So then our universal set in that case would have been the letters in the English alphabet. So we usually use a U, and your book uses a nice scripty or cursive kind of U in order to write the universal set. Okay, so that starts our vocabulary. A few more terms in the next part.